at seasonal timescales. So that is actually true for any other timescale as well. So then what are the strategies we have followed in trying to improve the skills in the models? And so still there is a lot of way to go forward further for improving it further. So what is the roadmap for future improvements? That also we'll talk about. And so monsoon mission is a national mission mode project of Ministry of Earth Sciences. So it started in 2012. So it has completed 2 phases already. So in the first phase, what we did is that we just borrowed a model from NCEP. NCEP is National Center for Environmental Predictions in USA. So then we try to look at how well the monsoon is simulated and what are the skills of the models. Like that, we try to look at the models. So before that, we have done an exercise of understanding what are the present models at that time, 2012. What is the skill of the models? So this is very famous paper by Gilles and Srinivasan, which was published just before monsoon mission started. So what they have done is that they have taken standalone atmospheric model and given the observed SSTs, force the atmospheric model with observed SSTs. So, and this is the period from 1985 to 2004, they have carried out the handcasts. And if you look at the skill of that models, the maximum skill you can achieve is about 0.20. So actually this cannot be called as a forecast skill because the observed SSTs are used to make the forecast. So basically it should be considered as a potential predictability limit. So that is if you are using only atmospheric model. So if it is 0.2 means we know that not a useful forecast can be made. So then there have been, IMD has a long history of making seasonal forecasts using empirical models. It's almost 150 years old organization, and they have been using empirical models to make the forecast. And if you look at for same period, the skill of the models is about minus 0.12. That means as good as not having it. So then the coupled models. So coupled models were started being used very efficiently at leading centers that time. So though coupled models are having a very good skill in predicting ENSO, but when it comes to monsoon, the skill is only 0.09. So this is the benchmark when we started the monsoon mission. So we know that these are the skills we have to improve upon and try to understand how do we do that. So this is a paper by Wang et al. So he has shown very clearly if he is taking a period of 1989 to 2012, the correlation using the coupled models is minus 0.12. That is what is shown there. And if you use clip models, is 0.24, and statistical model and all. This is for another period, it is 0.09. So this is the way they are said very clearly that. And the reason Bin Wang et al. They gave a reason is that because there are 2 modes of ENSO in the tropical first week, and present day models are unable to get those 2 modes correctly. So that's why monsoon prediction is very, very low. So with this background, we started working on monsoon mission and started trying to find what are the problems and how do we resolve them. So this is the model borrowed from NCEP, and also COLA also helped us in getting this model. So we started the atmospheric model of the borrowed model is actually about 100 kilometer resolution, but we have changed it to 38 kilometer. That is one thing we have done. And there's a novel land surface model, SIS, CIS model, a coupler. A coupler is hard-coded, means each and every grid of the atmospheric model is hard-coded to the ocean model or land model. So it was very difficult to make any changes to this model. So that is another challenge. And ocean model, when we started working as the MOM version 4.0, and it was about 0.5 degrees everywhere and 0.25 in the tropics and 40 levels. So this was the system that was made operational at IMD also after making some improvements in at least increase the resolution. So what additions we have done in this model framework is that we started generating our own initial conditions at, for example, atmospheric initial conditions. We started taking it from NCMRWF and ocean initial conditions from INCOIS, Hyderabad. And the runoff is very crudely prescribed. That is one value for throughout. So this is the model that we started using it. And actually, once we have increased the resolution itself, we started getting very good results itself. So whatever we have seen 0.2 in the atmospheric model has jumped to, our 0.09 couple model has jumped to 0.47 or 0.4, about 0.5 almost in this model. So if you look at the problems with these models, that though I am mentioning that these are the problems for CFS model, but these problems are there for any model, any couple model you take across the globe. So these problems are there everywhere. So what is that? The cool SST bias in tropics, except in Eastern Pacific, you see that there are two blobs of warm SST bias in the tropical Pacific and dry bias over inner landmass. You can see that T126, we used to have very strong, almost 80% bias. If it is 8 millimeters per day is the seasonal average, we used to get about 2 millimeters or 3 millimeters per day. So that was the, so this almost, there is no monsoon over Indian region. So when we increased the resolution to 38 kilometers or 35 kilometers, then the bias started decreasing a little bit. And SSTs also started warming here and there, but there is no clear pattern. So then also the diurnal amplitude. We all know that the diurnal cycle rectifies into intraseasonal scale and intraseasonal rectifies onto seasonal. So if you look at the diurnal amplitudes, the phases, they are not very well captured in these models. Again, this is not only for this model. You take any coupled model across the globe, situation is same. So though they are having different flavors of the same thing, but every model suffers with the same biases. So there is no single exception to that. Some may be having very serious biases, some may be having less biases. That's all the story. So the another one is ISO to total variance is overestimated. So ISO is so much of very strong in the couple models. So by looking at all these things, then we thought if we have to make a strong impact, so we have to address these biases at least and try to see how we can address these biases. So as we said, we started working on different schemes. So Partha is here. He is the one who has introduced us to new SAS scheme in the MMCFS model. So you all maybe by now fully familiar with what is the Arkawa-Schubert scheme and Arkawa-Schubert to how it has become SAS. Then afterwards, new SAS is Han and Pan have developed this scheme, and these are the different modifications have been done. Convective trigger, cloud top selection, momentum transfer, cloud bakes, mass flux, all these things have been modified so that you get where you need to get the convection, that right place at where there is updrafts, that is where you should get that. So also increase the convection strength. All that happened because of new SAS. Then we only realized like that we have done several experiments actually. So there are more than 60, 70 model sensitivity experiments have been carried out to understand and reduce these bias. So I'll just give you some of those examples. So you can see that A2O is there, but beyond there are so many, but I'm not showing all of them. So this is the control run where we have done the handcast is 2003 to 2017, and the resolution is, so one thing that we have always done is that whenever you do the development work, carry out first in the low resolution model, T126. So if it is successful, then use it at high resolution. So this is the philosophy we have followed throughout. But some of you can ask, what is the guarantee that whatever worked at low resolution will work at high resolution? But we all know that the computational resources are not infinite. You have to work with what is given to you, so that when you are doing so many experiments at very high resolution, data management will become a big issue, and also the computational resources will become another issue. So that is the why we have started following this strategy, that first try to implement everything in low resolution model, then see it how the high resolution model is getting benefited afterwards if we are really. So when we see that these are the skills of all India summer monsoon rainfall with GPCP as the reference point. So what all we have achieved, the skills have improved, is brackets we are given what is the increment in the skill when you have implemented a particular scheme. So this is the control run that is done. So it was 0.33, and the improvement after correcting some of the bugs, we have borrowed models, so that we started getting about plus 9% improvement in this one. So again, the NCEP model, whatever, using the NCEP initial conditions, here we are using our own initial conditions. If you use NCEP initial conditions, this is the model. But you have to notice that the handcast period varies from one run to other run. So whenever we are making comparisons, we are taking exact same handcast period to make the comparisons or the improvements. Okay. So there is a COLA also has identified several bugs in the model, and they have given us, and when we do that, skill is not so promising, 0.29 only. So then these are the 4 experiments which I have done on convective parameter scheme by doing several SAS2 and adding shallow convections, all those things. What you see very clearly is that when you actually work with convective scheme, the skill jumps by almost 91%, means almost doubles. So that is one good thing about this one. Then we realized that we are getting these improvements for wrong reasons. So you have to get the things correctly for right reasons. So what happened when you try to do this, because the clouds are increasing as expected in USAS, and convection is increasing, the amount of solar radiation that is reaching surface is decreasing significantly. Therefore, the cold SST bias that we have seen before is becoming worse. So actually it is raining over cold SST regions. So that itself tells you very clearly that we are getting something wrong. But the results are very encouraging. So then we realize that it is one most important improvement that we have to do is in the convective scheme, and that has to be there, and try to find out what are the other ways of alternate ways of improving these other biases that are cropping up because of this. So our new version of the model has this new SAS scheme, but your SSTs are now reasonable. So we have done all that changes. So there is another run we have done, the albedos prescribed from the satellite observations, where the non-ice albedos were prescribed. And this is the only development that has resulted in reducing the skill. Almost 60% skill has dropped now. So maybe it is the fine tuning because of these albedo effects has now taken fully into that account, but all other models have shown clear improvements from the control run. So the other one is if you have used only inchoate initial conditions, then also we get 42% improvement in the. So what is that? The NCEP initial conditions and our own initial conditions shown a lot of improvement compared to what NCEP uses. So because the techniques of creating the data simulation also different in this one, though we have borrowed from them, but we have improved upon those estimation techniques. So this is the high resolution. High resolution also 0.51 is the scale, that is about 76% improvement. So one thing that you notice from all this slide is that there is a lot of developments have happened, and almost all development activities that we have taken up are showing improvement in the scale. So Nino 3 also, you see that some good improvements. Once we have added SAS, you get 0.7. So, but the problem is that, as I told you in the beginning itself, this is a hard-coded coupler. So if I have to incorporate all of these things into the borrowed model from NCEP, then it is almost impossible. So what is that we have to do? Then first thing, we have to remove that hard-coded coupler and bring in a very friendly coupler where you can add several components. So that is what we have done. And again, fortunately, the new version of the model shows much better skill than any of these developments. So in spite of all these efforts, there are some intrinsic challenges that are there for predicting monsoon. So that should be very clear to all of us. So how do we make this forecast, and what are the intrinsic challenges that are there? So this is a slide from Professor Shukla, who gave a lecture in IIM Madden-Julian lecture in our institute. So he has shown very nicely that the anomaly correlation coefficient of the coupled models from the same model is reaches about 0.8 in recent periods, whereas it is 0.7 in the earlier periods. You can easily attribute this to the observational network that is there, Tau observational network that is there in the tropical Pacific, that has really made a difference to the skill of the models because the initial conditions are better. Whereas if you look at, this is Nino 3.4 scale and this is monsoon rainfall scale in the same model that we borrowed. So you see the difference between SST prediction that happens in the tropical Pacific is 0.7, whereas when it comes to monsoon rainfall prediction, it is only 0.2. So that actually exactly matches with the first slide that I showed you. So this is the big gap that is there. So that is the reason the world community is so much afraid to touch about monsoon. The simulations are difficult, improving skills are difficult. So once upon a time, WCRP, World Climate Research Program, identified monsoon prediction is one of the grand challenging problems. But within 2-3 years, they have removed that grand challenge. The reason is simple, because no breakthrough is happening. So that is the reason why we have started monsoon mission. So this is our problem, and we have to address that problem. So if you look at again JJS, this is for shorter period, it is 0.29. This for longer period, 62 years, it is 0.29. In 62 years, the ENSO monsoon relation was very strong in these years. So even the statistical models used to work very better. The skill used to be 0.9 because only ENSO used to determine your monsoon. So as I mentioned in the previous slide, ENSO is the major modulator of interannual variability of monsoon. That we all know that, correct? So, but the biggest challenge is that in spite of knowing that ENSO is the strongest modulator, we have to make forecasts of ENSO in the spring. So this is the variability explained by different initial conditions. If I use February initial conditions, the variability that I can capture in the coupled models is about 5 to 10%. March may reach about 30%, April is also about 30. So, but if you come to summer months, the variability explained by these initial conditions is more than 60 to 80% or sometimes 90%. So making a forecast in the summer months, trying to predict December, January, February SSTs is much more lucrative, means the forecasts are much more reliable. So what we call this less variability explained with these initial conditions is the spring predictability barrier. If you initialize your models in the spring, then ENSO skill will not be very good. So in spite of strong association with ENSO, but this is the problem that is intrinsic problem. This spring perturbative barrier will be there, though some people show that in some of the models it is gone, but it will come back very soon once they change the hindcast period. So this is the biggest challenge. So how do we address this challenge? Until unless you try to improve the prediction skills of this season. If you use initial conditions from the spring and try to improve the skill of the ENSO, you cannot make appropriate monsoon predictions. So this is the challenge one. So this is what all of you students, particularly the scientists, have to look at. How do we address this problem? Okay, this is the challenge number one. So if you look at, if for example, these are the CS5 20th century simulations are done. So if you look at whenever we start forecasting the spring, the skills are much, much lower. Whereas if you start with summer, the skills are much better, reaches almost 0.8, 0.9. So only in recent periods, they started improving, but not as good as before. So the challenge number two is that what is shown here is that the standard deviation and standard deviation mean ratio. Standard deviation is shaded and ratio is are the lines. So if you look at only 20% of variability is seen, or less than 20% of the variability is seen over the monsoon. Whereas if you look at tropical first week, the variability is much more than 60%. So the signal itself is very strong elsewhere. Whereas over monsoon region, the signal that we are trying to capture is very, very weak. So if you look at the all India summer monsoon rainfall, and the deviations are plus or minus 10%. So the standard deviation is only 10% of the mean. Okay, so here you are showing 20%, but mostly over the oceans. But the same ocean in the same latitude belt, you see that when it comes to first week, it can explain 60% of the variability is 60%. So predicting something like this is much more easy than where the signal itself is very, very weak. Okay, so it is a blown up map, and you can see that over Indian region, it is not much variability. So the challenge number three, so you cannot change that at all. The challenge number two, you cannot increase the amplitude or the variability so we have to work with that only. So the challenges, they will be there throughout. No matter what development you do, these are the challenges will remain. So we have to find ways to address that. So this is another biggest challenge. Though ENSO monsoon relation is very strong, but these models, different models are there here. They actually, this is only MMCFS is shown, but it is, again, you remember that whatever I show you here, the problems are same for across the models. So they show very clearly JJS that, these are the observations. The correlation is very, very weak actually in the recent periods. But if you look at the models, they are doubled or sometimes triple. So there is a strong ENSO monsoon association in the coupled models. So how do we address that? This can be addressed, but not the first two challenges. Okay. So then we notice that is basically because when the synaptic variability, that is low pressure systems, are very, very strong in the months of July and August, that coupled models are unable to get them properly. So the synaptic variability is completely missing in the month of August. That is the reason what we notice that unless you improve the synaptic variability in the models, the ENSO monsoon relation will not improve in the models. So the other challenge number 4 is this is coming from that only, the earlier slide, where the synaptic variability is contributing to ENSO monsoon overestimation of the relation. And if you look at these different, this is GPCP, MMCFS, CCSM, 4 and floor B, GFDL floor B models. So this is the total variance and June, July, August, September, and JJS together. So this is the ratio of synaptic scale 2 to 10 days band pass filtered variance to total variance. So this is the monsoon band. You can see that everything is underestimated in the couple models. Somehow floor B, GFDL floor B gets some of the variability. So, but in that model also the ENSO monsoon relation is again overestimated because it is actually underestimated in spite of doing better than other models, still underestimation is there. So basically what we have learned from all these challenges is that the most important thing to improve the monsoon forecast is that look at small scale. Not only spatially, in the temporal also. Until unless you try to improve the dynamic cycle, you cannot get seasonal mean much better. And similarly, if you don't resolve the eddies, particularly in the oceans, particularly in the Bay of Bengal. Bay of Bengal, we all know that it is highly stratified basin because the fresh water that is coming from the rivers to Bay of Bengal. So therefore, it creates much more eddies compared to any other basin. So how do we get those eddies? So these are the lessons we have learned, and we are able to address challenge number 4 and 3. But 1 and 2 will remain forever. So this is the new version of the model. We can call it almost Indian version, but I should say very clearly that individual components are developed by somebody else. So for example, MOM version 6 model is developed by GFDL and GFSL was developed by NSAP. But here again, Parthasarathy here, that group has done changing the dynamical core TCO. So that once we couple this to this, then it becomes much more indigenous model. So then you can ask, why are we using still models that are being developed elsewhere and bringing it? So we don't want to again reinvent the wheel. E is equal to mc square, is equal to mc square, whether you do it or whether it's done outside. Okay? So we have to take it from where some foundation is already there. So that is the principle we have followed in the monsoon mission. We don't want to rewrite the whole equations and momentum equations and try to solve them. Okay, so we have biogeochemistry, and good thing is that now we have also aerosols in this model. And so one good thing is that we have a river routing model and also core 3 flux algorithm, and we are trying to add ocean wave model as well. So these are the different things that have been added, and you can easily call it as an indigenous model because a lot of developments have happened. And in fact, after we have done this work, the other centers like GFDL, NCAR, they started implementing these things. So actually river routing model was there in the long simulations, that is climate projections runs. But then nobody has ever used it at seasonal scale. So that is what we have done in this model, and we have shown that particularly Bay of Bengal stratification is very important. Until unless you get that stratification correctly and the eddies in the Bay of Bengal correctly, you cannot improve your monsoon simulations. So the people started asking us, how did you do this? And what is the code changes you have made? So how you have taken the budgets and all that. So we have provided guidance on incorporating this in other models now. Okay, again, core 3 was there for a very long time. Core 3 is a flux algorithm. So we all know that most of the models use bulk flux or NCAR flux algorithm. So we started using core 3 flux algorithm. And that has actually made a lot of difference for resolving the diurnal scale, diurnal amplitude. So therefore, the ISO variance, total variance ratio also started becoming close to observations. And the synaptic variability also improved. So, and most importantly, there is a development happened in the monsoon mission is that earlier, even now also, most of the centers do the individual component analysis from the atmospheric model and ocean model. So we have started working on weakly coupled, and it is now established that it does better. So, and that we are working now towards strongly coupled data simulation, wherein ocean will dictate that state of atmosphere will dictate the state of oceans. So that is being worked out. And once that is also incorporated, the skills started improving better, particularly at weakly coupled timescales. Okay. So these are the papers which are already published. We can have a look at it to get the more details. So this is the monsoon mission model, the first version of the model, and these are the different models across USA and also in the Europe. So this is the monsoon mission model. You can see that it stands out clearly from the other models. So you can see that almost all models are clustered together. The scale is still about 0.2, 0.3 only. This is the Taylor plot. And the variance is very much underestimated. Means the model is trying to get every time the normal monsoon. Like empirical model, it also gets normal monsoon. So the internal variability is not well captured by none of these coupled models. So for any model development, while developing, you can always call it as a very good skills. But the real acid test goes when you are actually making operational forecasts. So as I told you, we have started monsoon mission in 2012, but the experiment started from 2011 onwards. So these are the statistical model skills. This is the dynamical model, and these are the. So because this model was handed over to IMD, what they do is sometimes they use April initial conditions, sometimes March initial conditions. So mix up for various reasons. So operational, you cannot say that you have to use only this because of several constraints they face every time that they need forecasts, maybe sometimes very early. Cabinet will call for forecasts. So yeah, they have to give them. So the skills of these models, you can see that very clearly. First stage means the forecasts which are issued sometime in April. So these are actually real forecasts. Here, the second stage means already monsoon started. June, July, August, September, or August, September, they give that. So the skill is not really the skill of the monsoon. So the skill of the statistical model is about 0.33. Whereas if you look at dynamical models, with whatever setup IMD has, still it is better than statistical models. But if they have done what we have told them, use April initial conditions only. And if they do everything actually that, the skill of using the old version of the model is close to 0.6 and the new version is close to 0.75. So this itself will tell you very clearly, this is the acid test for any model and real-time performance. So even this, the number of years are not very high, but this is what it tells you very clearly, that 0.74. So you just imagine the first slide, 0.2 is the potential predictability using the AGCMs. Our coupled models 0.09. From there to 0.74, that is what is monsoon mission achieved. And this is the new model now. The number one is MMCFS version 2 new model. Again, it shows the supremacy compared to other models. Because what we try to do in this is that whatever biases we have identified, whatever experiments we have done, we try to incorporate most of them. And now you see that why this success, you can easily ask me why this happened so easily. It didn't happen so easily. We have done 50 to 60 experiments to understand what is required to be done. So the new SAS scheme, which was giving wrong results, for wrong reasons, it's giving right results. So now that also we have corrected. Now your SST is not cool anymore. In fact, it is slightly warmer compared to the, so warmer SST is expected to give more rainfall. So that relation is very well preserved in the new version of the model. So this is the skill that I showed you, that MMCFS1, GPCP and IMD. This is the internal variability of ISMR. The skill is, as I said, 0.722 to 0.74. And most importantly, so here it is not next. So the RMSE, if you make any forecast, what is important is that your RMSE, root mean square error, should be better than the standard deviation or less than that. So if your model has some errors which are much more than the signal itself, then it doesn't make appropriate forecast. That is true even for 3.4. Unless you normalize it, it is not going to give you correct results there. So, but one good thing that we have achieved is that the normalized root mean square error is less than 1 in the new version of the model. So that means the forecasts are becoming much more reliable. Okay. And this is the teleconnections with ASMR. Again, MMCFS, the old version, has 0.83, and MMCFS 2, slight improvement, 0.75, but still it is overestimation only. Still, we have to work on this. Observation is showing only 0.64. So still there is overestimation, but not as bad as other models. So this is one of the reasons why the skill is improving. Not only that, if you look at the skill of AMM at Atlantic Meridional Mode, then also it is coming very close to observations, 0.18 to 0.15 in the. So things have improved a lot, not only the SST metrics, but also the precipitation metrics. So the teleconnections started becoming better, not as good as observations, but better than what we started with. So that's why we started getting good results. So now, so when you say something like this, there are enough skeptics saying that you have selected a particular period, particular years, so that you want to show your model is doing better. So this is all reviewers. Myself will also ask the same question. So they also ask me the same question. So this is the first, when we published this paper, we have done it from 1980 to 2020. So we have shown the skill of 0.74. So then naturally the reviewer started asking, what is the guarantee that if you move to other period, this superiority that what you are showing still remains? So what we try to convince the reviewer is that we have plotted running sliding correlation for 11 years. And what you see clearly is that if you look at these models, so here I am showing you other next generation models from GFDL and also UK Met Office. Even ECMWF also I have it, but that was already published, so I'm not showing. But again, you see that MMCFS 2 gives you 0.72 or CIS5, that is UK Met Office 0.55. So still we are maintaining that. And for longer period, CIS5 is not there. So if you look at there also, you see that our skills are much better than GFDL sphere model. Okay. So even if you look at the sliding correlations, again, the superiority of MMCFS version 2, the red line, that is very clearly on top at any given window you take. And most importantly, there is the ISMR teleconnections undergoes different phases. So this is the observations. So it was very, very weak during the period of from 90s to 2000s, early 2000s. So the teleconnection is very, very weak. But none of the model gets that. Except MMCFS version 2 has some variations. They are not as good as observations. So if you look at GFDL sphere, it is almost constant. A line which is vary from this period to this period, that is the blue line, goes all the way without any variations. So that epochal changes that happens that are not all captured in GFDL sphere. But MMCFS version 2 gets some variations which are not as good as observations. At least getting that is a good sign. So getting here is another challenge that again we'll keep working. So there is a lot of work still open for many researchers to work on this problem. So that is about seasonal, and we have forecasts that have been done at extended range timescales also. And this is the same model, that MMCFS version model was used for this, but what they do is they take different ensembles from different physics components, Arkawa-Schubert, revised Arkawa-Schubert, Ferrier macrophysics, Javankar. So like that, they create a multi-model ensembles using different physics. Okay, and they are run at T574, then changed to T382. So that also has shown very strong improvement, particularly in the week 3, the forecast, particularly for the monsoon zone, where the most of the rainfall happens. You see that there is 88% increase in the scale compared to the previous version of the model. So all these things are happening because we started looking at monsoon very focusedly. So how to improve the monsoon simulations and how to improve the biases. Improve the biases means reduce the biases in the models. So that is the only success mantra here. So we are fully focused towards monsoon and try to see that how do we improve, keep improving that. But one thing that after this monsoon mission, whenever I make this presentation outside of India, so everybody appreciates that monsoon being the strongest convection center during summer. If you don't get correctly in your models, you are not going to get good results elsewhere else. So now, whatever grand challenging problem they have been thought for some time, then left it in between, they started now thinking that this is the only way we can improve the skills of other regions. Because it is very simple. You have the strongest convection center in the summer season sitting over head Bay of Bengal. If you don't have that in your model, how do you get the tail conditions correct? Correct? So improving monsoon simulations is in the interest of the whole world community, not just for Indians. This is the message they got it very clearly. And then how people started incorporating most of the things that we have done. Even Partha has done that stochastic parameterization, not stochastic, multi-cloud, multi-physics, stochastic parameter scheme that also they are trying to incorporate in NCAR model. So whatever developments we have initiated, everybody else is now started working on those problems because that is the interest of everybody now. So if monsoon mission is successful, that is one of the success stories. We are able to convince the global partners that this is the thing that you still have to get it in your models. So again, not only the whole monsoon core region, if you look at the subdivisions also, particularly week 3, you see that the skills are improved, particularly the central Indian region. So improvements are seen in every small domains like subdivisions also. So I think Partha will cover most of this, correct? Extremes and short and medium range forecast. So I just want to tell you that the monsoon mission, when we started, this is one of the first results we got, that whatever day 3 forecasts, the accuracy of the day 3 forecast used to be there before monsoon mission, we could achieve day 5 forecast with the same scale. That means we have gained 2 days lead time in making the same forecast with same reliability in the short and medium range forecast as well. So not only that, you can look at, there are different papers. As you increase the resolution, the skills have improved everywhere. And these are different ETS, PSS, HS skills. You see this everywhere, the message is same. That monsoon mission is able to actually gain lead time of 2 days in improving the forecast. Anywhere else in the world, it takes for 1 day to gain 1 day, it takes more than a decade. So within 1 decade, so we are lucky. We don't say that something great has happened. Here we have increased the resolutions, then we could get it. So it has happened within 5 years after starting the monsoon mission. Huh? Yeah. So now the challenge is to move it beyond 5 days. That is the real challenge. And he may be covering the extreme events, getting extreme events. Morning only send me a paper that nothing is good in the model for extremes. So that is another challenge that I have to add to my number of challenges. Okay, but that is workable by using other techniques as. So they also, we have started ensemble prediction system at very high resolution. At the time of we implemented, no other center in the globe are using at that resolution, that many members for ensemble forecasting system. Again, you see that these are the RMSE track errors, RMSE of track position. So as you can see that the ensemble, if you use, instead of using a single ensemble, you use the ensemble mean, the RMS is less in use ensemble forecasting system. So things have started working, and also extremes, though he says that here Kerala event he could capture by saying that the number of standard deviations is, but the model itself don't have the extremes, so its standard deviation itself is low. So he has come up with a mechanism where, okay, if it is extreme for the model, so can we use that information? So that way he showed that yes, we could get some information from for extremes also. But if you look at only physics part of it or quantum of rainfall, that still we are far away from the reality. Okay, we don't get that much of quantum of rainfall for extremes. Okay, so this is another important slide. Once the TCO was implemented at IITM, so at the same time GFS FE3 version, that is NCEP, they also started. So both the models have changed the dynamical core at the same time. So normally we have a tendency to believe that GFDL does better than us. That is for sure because they have a lot of experience. The people, number of people work on those problems are huge. So therefore, it is a good hypothesis thing that they can do better than our models. But then we have made a comparison of TCO with FE3. You don't see much difference between these two. If at all, day 3 and day 5, slight improvements are there. But I don't call it as real improvements. So with the limited human resources, limited computational resources, implementing the TCO has really made as good as some other leading centers. Okay. So this is the model development strategy that we have been followed for so far. So we have increased the resolutions. So that has really resulted in a lot of improvements because it is expected once you increase the resolutions, the small scale features are well resolved. So therefore, as I mentioned in the first slides, getting small scale is more important for getting the large scale correct. So that has really helped. And also dynamical core also we started semi-Lagrangian TCO. So that is all this have made a lot of changes to that. And also the MOM4 0.5 to 0.25 changed to 0.25 to 0.25. So resolution is giving some results. But blindly increasing resolution is not the answer at all. So until unless you improve these parts, initial conditions and physics. So there are so many other ways to do it, but what we are trying to do is, we are trying to do these components at this moment. Then we will go to ocean model mixing schemes. Now there is a AML based mixing schemes that are coming. So that also we are trying to implement. 4.3 itself, estimating the CD from different observations is very challenging. So what we have did, we have created a AML algorithm. Now we have implemented to decide some of these coefficients. So that is also is giving good results. But right now I'm not going to show it because it is work yet to be published. So we also have done microphysics in different models, convective parameters, and all these things we have been doing it. Now the roadmap is keep improving these things, then try to get this also. This is the new paradigm shift that we all have to think about it. So how to bring in AML models, make use of them best, so that most of the things that can be addressed by these things also. So in fact, I'll show you next slide. Okay, these are the different AML models. You have forecast net, GraphCast. This is the GraphCast skills for different regions, homogeneous regions over India. This is all India. So GraphCast is doing definitely better. You take any time, day 1, day 3 forecast, day 5 forecast, or even day 7 forecast. GraphCast does much better than our traditional models. So when it comes to forecast net, if you use, this is the forecast net model. If you use only Indian data, the skills are not as good. So that itself tells us very clearly that even though it is short range forecast, but the reality is that you need to have the large scale or the global scale phenomenon into the model. So once you use global, then the skills are better. So these are the lessons we have learned from these AML approaches. So there is no way we can get rid of AML models because they are showing very good results, at least short and medium range. So STS timescales, seasonal timescales, they're yet to evolve much better way. So whatever skills achieved by AML models are as good as the traditional dynamical models for S2S and seasonal, maybe decadal also. Okay. So these are the AML. We have to take it very seriously, and each and every component of the models, each and every step of the model, like creating initial conditions, post-processing, everything can be done by using AML. So that is the way forward for improving the skills further. Particularly, one thing that I want to tell you is that if you are trying to increase the resolutions, now we are talking about exascale models at 1 kilometer resolution. So developing are something, so at 1 kilometer also parameter schemes will be there for some reason, for some components, okay? So, but getting observations at that scale is almost impossible. So then still we have to use AML. Then you can ask me a question, if you don't have the enough data, then how can you create AML models? Then you have to go to physics informed neural networks. So there are ways of doing it, but actually in India, we are yet to take advantage of this in a very big scale. Okay, so this is the things that will change a lot of things that way, the way we do it. Even the TCO model or our MMCFS version 2 model takes more time to run the model compared to the old version. But you know that operationally, if you have to make a forecast, you have to give the forecast before the event happens with long leads. So that again can achieve through AMLs. So to understand where the model is getting problems and how to make the faster. So this is the roadmap that we have to, all of us have to think. So recently we have started one Prithvi AA program in ministry under as a part of Mission Monsoon. So, but this is nothing to do with the AML models that are being incorporated in the models. This is the dissemination of the information. So what we came up with is that, like ChatGPT, we have named it as Monsoon GPT. So create the models, first use the large language models, then move to large multi-models, so that impact assessments also can be done, or impact-based forecasts also can be done by using multi-models. So I'm not going to give you more details because it is an NDA between the industry and us. So we are not supposed to give more details, but something like ChatGPT, Monsoon GPT is going to come, and it will be reality very soon. At least we are targeting for next 2 years, at least a prototype of Monsoon GPT be ready. So this is the message from the presentation. Dynamical models are really improving. It is not that they are stuck. There's a lot of improvements, a lot of scope for improvement. And we have shown in examples how to improve them. Definitely, convective parameters is one of the bottlenecks. The whole agenda of this workshop is that, and getting that correctly for right reasons, if you're getting good results, that is the most important message. So if you have to accelerate the growth, so now 0.74 is reached. So reaching from 0.74 to 0.75 or 0.76 is going to be very difficult. So that can achieve only through AML, by marrying AML to the dynamical models. And the Monsoon GPT, we are targeting in next 2 years to get a prototype. So actually this has come directly from Prime Minister's office, that we are always, as a weather forecasters or climate forecasters, what we do is we just display our information over website or through some app. But the real information, that is actually we are pushing the information. So what the Prime Minister actually gave a direction to the Ministry of Sciences is that You have to pull the information. Like, for example, a farmer is there. He don't know where to look for. So you just have to ask you guys or the app or anything that, can I do this practice of sowing the seeds tomorrow? So you should get an answer. So that is the pulling of the information by the farmer. So we have to get ready. So that's why this is the challenge given from by top. So we are working on that. So if you want more details, here itself you see that there are 50 others. So this is the publishing BAMs. The second phase of the monsoon also is now being prepared for BAMs again. So you'll get almost all the results that I have presented from these two different. There's a Clever Exchanges dedicated issue for monsoon mission. There also you can look at it. So this is one good thing that happened. There is a ICTS-TIFR, is a agricultural center, international center. What they do is they take the forecast from us, both extended range, short range, seasonal, and brief the farmers. If there is a delay of 2-3 days, the farmers will keep asking them, when are you coming to tell us? Because they have to. So that reliability of the forecasts have improved. That's why you see this is only one place. Like that, they do it for 4-5 districts. So the reliability has, particularly at least the people's mindset has changed that, okay, at least if you use this forecast, we will be benefited. Okay, with that, I thank you again, the organizers, for inviting me. If any questions are there, I'll take. Thank you.
Thank you, Dr. Rao. I think we have a few minutes for questions.
Yeah, you can speak loudly. Okay.
Thank you, sir, for highlighting all the problems, all 4 challenges. And I saw from the presentation that you relied on high resolution and some teleconnections to resolve the challenges. So my question is, do we have correlation matrix for example, sometime high resolution is capturing local phenomenon and giving a better forecast, but sometimes teleconnections are necessary for that. So do we have a correlation, weighted correlation matrix between them for a prediction?
So we have not done the way you are asking, but in our papers we have explained very clearly that once you improve the small scale features, so there is one paper, what is that LPS paper? Where is it submitted? IJOC. So that paper shows you that resolving the small scale eddies in the Bay of Bengal or the diurnal cycle. Diurnal cycle is already published. You can see that paper by Pradhan et al. So improving that actually improves. So we have not tried to segregate this so far, but that is a very good idea, and we'll try to look at how to address that problem. So whether the increasing resolution has made the change or the teleconnections. It's a good idea.
You can also learn by AIML model, as you are saying.
Yes.
And the other question, sir, can we go back to that slide, the new forecast system? Yeah, this one. Here, I want to understand the bias part, where the biases are in all the models, whether atmospheric model, land model, biases are everywhere assessed and corrected, or we are correcting the bias only after forecast? I'm not.
Okay. So the biases are there if you are looking at an individual component. See, for example, I am telling you that there is a strong dry bias over Indian landmass. So that is in coupled models. So we try to understand whether it is coming from the ocean model or atmospheric model. So in fact, atmospheric standalone model gives you over estimation of the rainfall, at least first few days. So afterwards only error will grow. So then we realize that it is mostly, say once you look at seasonal scale, the ocean plays a very important role because memory is there. So we try to improve the diurnal cycle in the ocean model, SSTs and all that. So it is a very tough job, very involved job to understand from where it is coming and what we have to do. So each and every experiment has been done by following that criteria.
Sir, if one has to do bias correction by data-driven way, so is there any way we can access this atmospheric model, line model of?
I will be very happy to give you that.
Thank you, sir.
So there is a ARDC website, ardc.propmed.res.in, correct? Or you just Google it, ARDC IITM. You will get that data center. And if you ask for a particular data center, we will upload that also.
Okay, last question. Bias needs truth and forecast, right? Observation and forecast to correct the bias. So what are the reliable data sources for that? Specifically, I'm asking about forecast because observation data sets are there. So forecasting data where we can get.
That is where the ARDC will get that forecast data.
Okay.
So all our short and medium is being uploaded every day.
Okay.
Seasonal, once in a month. So for some reason, you think that the variables that are given there are not sufficient. You want more data. You can always write to, there is a email address there that I want this data to be uploaded. So within 1 month, they will upload the data.
Thank you so much.
Okay.
Yes, thanks.
Yeah, thank you, Dr. Rao. That was a very nice talk and very encouraging to see the progress that's being made. I was wondering about the hybrid strategy that you mentioned with the AI and the dynamical one. And so nowadays, when people say hybrid, it could mean multiple things. It could be just having data-driven models in an ensemble, or it could be nudging the dynamical model with a different data-driven model. It could be AI components within a model. And could you elaborate on the strategy when you mentioned this hybrid?
So the basic thing that I'm trying to tell here is that hybrid means you have to use both the dynamical models, the forecast made by the dynamical models, and the AML models, and also incorporate these AML in the parameter schemes. So that is what is the hybrid nature of this AML. If you try to train your model only based on observations, for example, you try to predict extreme rainfall events. That never happened in the data period. Okay, so you don't have that information in that data. So that information you could get better way from the forecast. What Partha has developed, that if the model itself it thinks that it is extreme event, though it is not exactly extreme as per the observations. So that information has to be used, then only you can make a progress in. If you use only data-driven observation models, I don't think you can make.
So in this case, it would be having an ensemble of both dynamical and data-driven models.
Yes.
Yeah, which we guess that the prediction of extremes would be better by dynamical.
No. If you don't use the information, train the models using the dynamical models, then I don't think you can get better information. Not just create the ensembles with AML models, which are driven only by the observations.
Yeah.
Try to do that hybrid approach. As far as my understanding goes, it will not work.
There's time for one more question. I was wondering about, so in the first half where you showed the comparison of the MMCFS and GFDL with the ENSO, and you showed that the correlation of the GFDL model was just
flat.
Yeah, I mean, there's no variability there. So there is variability in the MMCFS, but it seemed out of phase with the correlation of observations.
So first step is to get the variability. Okay, so then try to get the phase also correctly. So this is what we have achieved. The next step is to get the phase also correctly.
Okay, yeah, thank you.
See, all problems cannot be addressed in one single go.
Thank you, sir. My question is same parameterization scheme used for different resolutions, or is it necessary to modify the parameterization schemes?
There are actually
based on resolution?
Different. So MMCFS version 2, we have a scale-aware parameter schemes, both in the oceans and the atmosphere. So you have to change. But when you go to the 1 kilometer resolution, that is what I was telling, that AML has to come to your rescue.
The next question is, scale of the forecast is defined as correlation between observed and predicted anomalies. So why is it so, and why is it not defined directly based on the difference between observed and predicted values?
RMS is also there, no? I shown.
Thank you.
Any other questions?
See, there are so many metrics to estimate the skills, but easy way to communicate is through correlation coefficients. So that way you can easily connect. So there are ROC curves and all that, but you try to complicate things.
Any other quick questions? Maybe, yeah, okay. Just keep it quick.
Yeah. Physics informed?
Neural networks. You have mentioned physics informed neural networks can be the future for forecasting. So how is
that is what we believe, because nobody has ever tested so far. So that is the move forward, the way forward to improve that. Because as I said to his question, you don't have extremes in the observational records. So if you get some information from your dynamical models that my instability is going like this or moisture conversion is happening like this, then can I get a extreme event of this magnitude? So that has to be through physics informed.
Thanks.
Yeah, let's thank Dr. Rao again for a very nice. So
Done? So, good morning. Good morning to all of you. Yeah. Tell me one thing. If I show the pointer here, the online participant can see my pointer? No. So, so I will use this, okay, cursor, because otherwise there is a communication gap. I tell something, they are blank, okay? Yeah. This I learned from virtual talk, webinar, okay? Yeah, so, yeah, what happened?
Not showing online.
No, not showing. I don't know, they have some, yeah, okay, yeah, I'll do that, yes. The pointer must be here, right?
Okay.
Pointer option. Laser pointer, right? Okay. Let's start my stopwatch. Okay, thank you. So thanks to organizer, Dr. Vishal and all others. A very promising workshop. I appreciate. And I wish that you, the next generation, continue this. Okay, we tried a lot. I conducted two big conferences, 2017, 2019, and so on and so forth. The purpose was, I feel this model developer is an extinct community. Okay, I don't find people, students, they are interested. They're all interested to analyze CMIP 5 and CMIP 6. Get paper quickly, get PhD quickly, then get postdoc quickly, everything quick. Now AI/ML is there. Things have become even quickest. Okay, there is no time for anyone to develop model. This is one way. People hear Eric or stalwarts. So and then they get motivated. Okay, said, yeah, this is an open field. We have to contribute something. So that due to that purpose only, we conducted so many workshops, and now you are conducting this. So a big appreciation. Thanks to Surya, he has made my job completely easier. Okay, so I can now play around in the ground, and you can see all my collaborators. Okay, nothing can be done without them, and so now I have been told to talk about extreme, and you have already heard it is very extremely difficult job to predict extreme. Okay, so anyway, but at the same time it has to be pedagogical. That's what is told. So let me start. So this is my outline. Okay, so I'll give a very brief. I think you already must have known, but still, I'll give a very brief basics of NWP and convective parameters and bottleneck. So since yesterday you have heard, one statement many times: moisture and precipitation, relative humidity and precipitation. What I understood from since yesterday that things are happening some way in observations, things are happening in some other way in model. Okay, and whenever we are trying to compare these two, we are getting embarrassed. Okay, model is not capturing what is happening in observations. So now that is considered to be a bottleneck. Since when this bottleneck exists, and what are the way out, and what's the consequences? Okay, and then I will talk about the new approaches, and then the future, way forward. Now, Daihum yesterday started with the figure of Madden-Julian. I think anybody who's tried to speak anything on NWP, they must start with this picture. Those of you may be knowing, those of you who do not know, I mean, take note of it. So this is the famous, team of ENIAC computer who first tried the first, NWP forecast. And you can actually see, so you can, of course, get this picture from various places, but there is a BAMS paper by Peter Lynch in 2008, where this picture is really very clear. You can see von Neumann standing here, and Jules Chern is standing here, and Fortov standing here. And the first model that they used, that Peter Lynch called CFVN, okay? So it's like Charney, Fortov, von Neumann model. And this is the forecast, okay? And you see what is written here. NCEP-NCAR reanalysis helped show that that for historic forecast made in 1950 with a pioneering, ENIAC computer, all had some predictive skill that he's telling in 2008, okay? And with a minor modification, they still might have been still better. That's what Peter Lynch comments. So this is a forecast, okay? Very interesting. This is the initial conditions, okay? Two lines, thick line is the geopotential height, and the thin line is absolute vorticity. This is IC, okay? This is the 6th January 1949, 500 hectopascal, 03 UTC. This will be the verification. This will be the target. So 24-hour forecast, okay? And this is actually what they did. You can see the changes, observed changes, okay? And forecast change. So solid line is observed change. So this is basically the difference between these two, and the dashed line is the forecast change. What broadly you can see, even not, if not very clearly, the dash and solid, they are kind of coinciding each other. So that itself shows the forecast change and observed change, they're kind of coherent, right? And this is the forecast. Okay, this is the forecast again of height and vorticity. Actually, Peter has done a good job. He has created the same figure in a much better way in the for all of us to understand, and he has put different color. The message from these two is that even in 1949, with a very simple broad tropic model, they could forecast. Okay, and I will in a minute I will show you. So what is the situation even after that? Okay, so these figures, I think equations are known to you. 120-year-old equations still valid. I heard some mathematician is telling, in a very microscopic scale, this Navier-Stokes fails. First time I heard in my life the Navier-Stokes equation fails. Where? Yeah, I heard this lecture in academy. Anyway, now this is the equation 7. That's we heard since yesterday, many times. Okay, I will also deal with that, and Surya also has dealt a lot with that. In principle, they are closed. In principle, they are solvable. But the issue is these red circles, okay? F, Q, and E minus C. And you see what Jules Charny in 1949 in his paper, I just copied the abstract. Please read this paper. My request to you is read every day, read one paper. Every week, read at least 2 papers. Don't leave the habit of reading. My earnest request, whether there is ChatGPT, IML, please read. Okay, what Charny has told, the small scale noise disturbances of the atmosphere create difficulties for the numerical integration of the equation of motion. So he in 1949, and Surya also discussed just 5 minutes back. So this noise and this disturbance, the small scale disturbances, so he realized in 1949. We are also realizing we are very, very serious, but we are helpless. We are, still repeating the same thing what 1949 he repeated. Okay, this itself shows that we have progressed slow. Okay, this is the bottom line. The progress in this field is very slow. Okay, so we need more people, we need more brains, we need more, talents. Okay. So this is one. Okay, now go to the next. So these are basically the quantity which we parameterize. Okay, F, Q, E minus C. That's all. And you can see all things, all types of heatings are included here. All types of source and sinks are included here. And there we falter. Okay. I'll skip this. This may be known to you. So now here in 1975, another thing happened. Orlansky, he first defined the scales. Okay, so we first, understood that okay, there are different scales, and these equations, those 7 equations, may require, some analysis to make it suitable for all these. Okay, so that was one development happened, and then, we meteorologists are very smart. We immediately thought, okay, so for each scale, like different, we have. Dress S, L, XL, double XL, triple XL. So we made immediately, okay, so for thousands and, for wave number 1, we will use global climate model. And for millimeter and turbulence, we will use DNS model and so on and so forth. So our all scales are ready, our all garments are ready, okay? But this has done another thing, okay? Oh yeah, so these are all sets of equations that Surya was showing we use in IITM, all operational center, they use a different model for different. WRF has some model for solar, WRF has some model for fog, okay? But eventually what happened is, this is a very important paper. I think you must read it, okay? Peter Bauer, 2015, Silent, Quiet Revolution of NWP. And you see, he has very clearly shown the error propagation across the scale. So you use more boundary, you use more compartment, you add more errors. okay? It's not going to solve your problem, it's going to increase your problem. That's why we have developed a new word which is called seamlessness. We have one model which we will use for, so many this thing. But one good thing, in this paper, he has shown very clearly that where we need parameterizations, okay, where we don't need parameterizations, where we need coupling, where we may not need coupling, where the computing resource goes high, where it is not so high. So in one piece, it's beautiful. Must read, all of you, okay? And this paper, there was a virtual field campaign. I don't know whether you are aware. So Mitch Moncrief and Dwayne Walliser, they conducted a virtual field experiment, YOTC, Year of Tropical Convection, okay? And ECMWF is a very precious data, okay? I don't know whether you are aware. Data is free of cost. ECMWF, somebody was asking for forecast. So ECMWF generated very high resolution forecast for YOTC purpose for a period of 3-4 years. Even they stored the tendencies, okay? This is a fantastic data set. I don't find any, if you go to Google right now and give a search papers on YOTC, you will find very less, okay? People don't use it. Students don't use it. It is free, okay? So you can read this paper, BAMS. So in this paper, again, if you see, Mitch has actually showed what Peter has also mentioned, upscale effect, downscale effect, okay? But what he actually, made a very nice framework is that he has connected diurnal cycle to seasonal cycle, what Surya was telling. And what he has actually identified a bottleneck is that the mesoscale system, which are actually responsible for convective organizations, the parameterization for that is missing in all global climate model. That's what he is writing here. He is writing here. Organized convection is not parameterized. This is one of the findings of YOTC. Okay, so I cannot go into the detail. Please read the paper. So he was mentioning about the WCRP Grand Challenge. Okay, this is the white paper. So our friend Pierre Sivesma, he and many others, they have written many things. But one thing, drew my attention. They said that lessons from observation and crowd resolving model. This is very important. They're writing it in 2012. Okay, AIML was not there, but now we understand that how important it is to learning lessons from cloud resolving model and observations. Now, question is, you can ask, are we learning? Are we learning any lessons from crowd resolving model and observations? So subsequent slide will tell about that. And Christian Jacob, in the same, WCRP, he also emphasized we should understand how model errors impact projections and predictions. So they both are talking in a WCRP platform two very important things, okay? Learning and identifying errors and learn from observations and cloud resolving model. Now we should prove, we should demonstrate that in 2024, have we progressed towards that? That's the question. Okay. Now this is a very, very, very common picture when you sit in the window seat of an aircraft and look outside and make an imaginary grid. You can see this type of organization where you can see there are clouds which are within the grid and there are clouds which are crossing many, many grids. Okay. So some are subgrid and some are grid scale. Okay. So I'm entering into parameterization now. Okay. Okay. Now this is, now I will mention 4 papers. Again, you should all read this. Arakawa Journal of Climate 2004, Arakawa et al. 2011, Arakawa U 2013, U and Arakawa 2014. 4 papers. You should all read. Okay. Now what actually Arakawa mentioned, you see here. Okay. He connected all processes: dynamical, hydrological, radiations, boundary layer, everything, precipitation, ocean land, but center is cloud. He said this cloud process is influencing every damn thing. Okay. So we need to improve this. It is center of the problem. And this, I will come more into this. This is a very, if you remember the WCRP diagram, this is basically his closure. He says the rate at which my large scale process supplies the moist convective instability, my cloud scale should consume it at the same rate. It's somewhat like you're driving a bike, okay? So the rate of supply of the fuel and rate of consumption of the fuel should be exactly equal, right? If the fuel supply is more, consumption is little oil spill, right? If the fuel is less, consumption demand is more, bike will stop, right? This is closer. 1974. We are celebrating 50 years, okay? Yeah, and so this is from Trenbath paper. So actually 3 parameters, 3 things we learned from Arakawa's paper. Arakawa's paper is very difficult. I'm reading now also, 1974. I don't know how many of you have read it fully, okay? Yeah, so 3 things we learned. What are all these things? One is cloud work function. What is this? This is nothing but moist static energy, instability, moist instability, cloud work function, okay? What is the second? Cloud-based mass flux. Have you heard this name? What is this cloud-based mass flux? This is something like, rho, sigma, and W, okay? Rate of change of flow of mass at the base. Sigma is the base of the cloud, W is the vertical velocity, okay? And density, cloud-based mass flux. And the third one is the convective quasi-equilibrium, okay? So this is cloud work function, and this is what is called convective quasi-equilibrium. Convective quasi-equilibrium is nothing but, the supply and consumption balance, okay? Now, so this is from Arakawa's Met monograph. It's there in IITM library, maybe they're here as well. So this is basically what he says is that the large scale ITCZ mean state, they supply moisture, okay? Large scale only supplies moisture. That's the control. It controls my moist instability. And this is cloud. Cloud consumes that, okay? After consumption, what will happen? It will give feedback to the large scale process. This is the heating. So it's the control, this is the heating. This is a closer, okay? But this is little more detail. Same from Arakawa's monograph. So large scale process causing destabilization plus means increase, moist instability, generation of cloud scale kinetic energy, okay? And then when cloud scale kinetic energy is done, then what will happen? Feedback in the form of warming and drying. Moisture source, moisture sink, okay? And then large scale process, this is a closer. So it's good, all good, well and good. But, so this is from the book of David Stensrud, okay? If you see there is a figure, 6.23 from a field campaign, they computed the synoptic scale supply and mesoscale consumption, okay? Just on a full field experiment. If you just add the synoptic scale supply, and if you see what is the mesoscale consumption, you see that they don't equal. They're not equal, okay? Now you see from where this mesoscale consumption is coming, Baba, okay? I don't see. Kahan se aa gaya? From where it has come? So there must be some local source. What is that local source? Maybe topography, Western Ghat, okay? Which my model doesn't see. But Western Ghat will add more supply, more consumption, okay? Local consumption. So Arakawa only considers the large scale, the grid scale. It doesn't consider the mesoscale. That's what Mitch Moncrief is telling. We are missing that, okay? That's why we are missing the extremes. Simple, okay? Okay, this is a good paper by IIT Delhi, maybe some PhD students. He actually put all the convective trigger and all the convective closures of many models. Somebody was appreciating French model yesterday, you see, and you can see here, you just look at the closer. All cape, all cape closer, okay? You see the trigger. Here also capes, relative humidity, that's all, okay? So there's no change, okay? It is same in CMIP6 as well. So then when I was in IITM, we thought that, Zhang already has shown the CQE is not good in tropics. Okay, we thought, okay, can we do it in model? Can we show it how the convective quasi-equilibrium? Nobody has done that actually. So Siddharth was working with me with our monsoon mission program, and so basically, if it is in if it follows the CQE, so my Kep now and Kep t plus 1, if I take different, it should be very less, right? Now and this is the same thing from monograph. Yeah, so this is the results. You see T126 and T382 CFS V2. One is 100 kilometer, one is 38 kilometer. What do you see? You see the decay, okay, is rather low. What does it mean? It means the model is very faithful. Model is faithfully following the convective quasi-equilibrium, what it has been told to do. Okay, what the reanalysis is doing. This is error 5, okay? And this is, so you see the error 5, you will find the values are much higher, okay? It's a reanalysis. So it means that this CQE is not holding, okay? It's not holding in nature. We are forcing the model to follow CQE, okay? What is not correct in tropics, okay? ARCO didn't have any other options, okay? But unfortunately, we don't have any option at currently either. That's the misfortune. We don't have any closure. If I ask you, tell me another closure when this is not working, we don't have, okay? So this is a forecast, it's very strange. You see, 2009, one of my students, we published this paper. We were doing a very simple experiment, maybe even simpler than what Charney did. What we did is, we took analysis. Okay, it was monsoon onset time. And we were plotting the, low-level convergence, okay? It's from analysis, okay? Low-level convergence. It is 200 hectopascal divergence, it is 850 convergence. It's simple. So when monsoon onset happens, you should expect low-level moisture convergence, upper-level divergence, right? And so analysis is showing that, okay? This is the time, okay? This is the time. Okay, we started from 28 May. This is the time of monsoon onset in southern India, 1st June. So we expect that, there will be a strong convergence. Look at the forecast. Okay, it's missing completely. So in 2008 and 9, what Surya was actually mentioning, it was terrible. Forget about seasonal. We are not even able to that. That's what possibly Peter Lynch has told. It's a fairly accurate 1914 book. We are not able to capture this 2009. Actually, it's for 2006. So this low-level moisture convergence associated with monsoon onset is not captured in GFS forecast. It's not our forecast, okay? We downloaded INSEP GFS and plotted. This was the situation. You have to keep this in mind from there where we have come, okay? We started from here. Okay, and now this is the recent 2020, okay? I think you must have already taken note of this paper, JGR atmosphere. So what is Bock et al. They have done is they're trying to quantifying the progress across CMIP, okay? So this is temperature bias, CMIP 3, CMIP 5, CMIP 6, high res MIP and low res MIP, okay? So even if you don't go into the detail of this forecast, you can very clearly see the northern hemisphere is colder, southern hemisphere is warmer, right? But if you see a little carefully, you see all the regions, okay, where you have low cloud, the regions of low clouds, okay, you see there warmer anomaly, okay? And there is not much difference between CMIP 3 and CMIP 6, okay? What does it mean? Okay, it means your model is showing higher temperature over those regions, right? Low cloud actually should cool the surface, right? If model doesn't have low cloud, it means it will allow more solar radiation to penetrate. It means it will warm your surface. So it means all these models are systematically underestimating the low clouds. Got it? The same thing is for southern hemisphere, which is a regime of low and middle cloud. The low cloud remains for weeks, months, and so on. You see warmer anomaly. And the anomaly is not improving. Actually, in CMIP6, it is looking, like somewhat more, okay? So this is directly related with cloud, okay? The mean state of cloud, what Arakawa said. I always hang around Arakawa, okay? This is my bias, okay? Yeah, but you can argue, see, in high res it is better. Yes, better, definitely better. But you see, it is cooler, right? I mean, at the same time, the polar, right? Sorry, this is higher, high res. Sorry, no, this is low res. Okay. Anyway, so the point is, the issue still remains, as Surya was telling, whether it is high res, low res, CMIP3, CMIP5 is cascading. Oh, precipitation is even worse. Okay, you can't see. So everywhere you see. So the most prominent, to my opinion, I think possibly Eric was showing the STIPEX experiment. This is a very prominent double ITCZ in all models, even in high res. Okay, and you see the global land. Okay, the global land is all dry, and global oceans are wet. Okay, the reason is the table. You see the table, everywhere it is Cape. It's a function of Cape, function of relative humidity. And the tropics, during boreal summer, you take any station. Today itself, after lunch, you can check. Boreal summer, take from Wyoming, take many stations, and just check the Cape values. You will see almost all stations will report 1000 joule per kg. It doesn't matter. But that doesn't guarantee that those stations are getting 10 centimeter per day rain. No. Okay. But your model will, because it is made to do that. Okay. It's a function of K. So it will trigger. It will keep triggering. Okay. And this is a manifestation. Okay. So you see that the legacy continues. And as he was telling, CFSP2 is either, I mean, neither it's an exception, it's also a family of, model. And you see CFSP2, 38 kilometer rainfall bias, you can see it's raining heavily over ocean, less over land. Tier 126, raining over oceans, less over land, and so on. Another problem is, see, he was showing about what is called variance, right? The models are not explaining the synoptic scale, high frequency variance. Why? It's because they underestimate very severely all the convectively coupled equatorial waves. Okay, the waves are only perturbations, right? Otherwise, our planet would have been very nice. Okay, these CCWs are actually they trigger. They are the causes of variance. Okay, and you see the CFS, Kelvin waves. Okay, equatorial Rossby wave, fortunately or unfortunately, overestimates, but MRGs, there is no MRG. Okay, so this is and if you I have not plotted for any other CMIP5. I mean, you can do an experiment. You can take all the CMIP3 to CMIP6 model, plot this, you will see the same result. You plot a very simple analysis. You do a coherent spectra of, I was telling someone, precipitations and zonal wind U850, okay? You do for observations, you will see the coherent spectra is very coherent for MGO and for all these CCW. CMIP models will not do that. Okay, so what does it mean? It means that your circulations, okay, your precipitations and your heating, they are not coherent. They are not talking to each other. They are not tied up. Okay, and anyway, so this is another example. You was talking of this thing diurnal. I will come to that. You see, I have just plotted precipitations and Wheeler scatter plot for observation, and three resolution of the model. And this is, I just plotted a straight line, say around 180 watt per meter square, which is corresponds to very deep cloud. Okay, you see there are very less dots. Okay, you can see no in T382 there are some more dots. Okay, possibly, but still the model is struggling to produce deeper convection. That's the message from here. And if you go to diurnal, you see here, so this is 5:30 observations, okay? The rainfall is lighter. In the, by 11:30, cloud gets deeper. Here cloud gets deeper, rain rate becomes more intensified, okay? The model, what it is doing is, it keeps raining in the similar fashion, okay? Whether it is 5:30, it is 11:30, 7:30, okay? Only thing is that T120 has lesser number of points, T382 has more number of points. Error is similar, okay? So you are actually magnifying the error. It is same, you get the broom structure, okay? So anyway, and this is the paper by Surja's group, where they showed that so as a result of that, the model produced a lot of convective rain, and there is you're left with very less moisture, which can actually give you stratiform rain, okay? So you can see all the models, they produce very less stratiform rain and very large convective. So this is the issue, okay? And this is the, I will skip, this is the, the synoptic variance. You can see in CFS, it is underestimated, and ISO, it is overestimated. And see, another issue is, this was a very old paper. See, rainfall comes in epoch, right, in monsoon. It doesn't happen that it keeps on raining whole season. You see, that's what observation is showing, right? So here is a rainfall, then there is a, drier, then again rain, there is drier. But you see, we have used three models, convection, BMJ, Bertz-Miller adjustment, Ken-Fries, and Grell. They keep raining. They keep raining. Because whatever cape is available, that's enough for the model to produce rain. So it will produce rain. That's all. So this is a recent paper by Siddharth, okay? What we did is you take GPCP or TRIM, do a Markov model, okay, calculate the transition probability of 4 states, okay? No rain to no rain, no rain to rain, rain to rain, and rain to no rain. What we find is model is always sticking to rain to rain. Okay, you see P11. Where is P11? This is P11 observations. Okay, and this is P11 for these two models. Hugely red. So model, if it starts raining, it remains in rain state. It moves to dry very slowly. Okay, so it's giving you wet bias. Okay, this is a problem. Okay, back to Arakawa. He suggested there are two possible, way of overcoming this problem. One is you go through multi-scale modeling framework, MMF. Other one is you develop a global cloud resolving model. This is the prescription of Arakawa in 2013. So following that, and also, this is the spectrum of cloud which has to be there in the model that actually influence your radiation. So cloud, spectrum, and radiations, these all have to be tied together. Then only you will get convective coupling. That will give you the waves, that will produce you the variance. Then you can expect something to happen in your means. So following Arakawa, we did this SPCFS. A lot of engineering. I'm not going into the detail. So originally, introduced by Randall and Witek. Okay. So basically, you put lot of cloud resolving model in the inside the GCM grid. Okay, and then this. So basically, these are the two equations. Okay, heat source and moisture sink. You compute that, and your dynamical time step is bigger because your GCM is say 200, 300 kilometers, whereas your CRMs is 2 kilometer, has 10 seconds, 15 seconds. So basically by the time your GCM takes one long step, your CRM takes many steps. So basically you are building a lot of statistics of heating source and moisture sinks, okay? That actually your convective parameterization does. Now they are not doing, the CRMs are doing instead. And by the time your GCM is ready to update that, you are asking the CRM, hey, you give it to GCM. So your GCM gets that. So basically you are resolving, you are cloud resolving subgrid scale processes. Okay. So if you do that, I leave this, yeah. So if you do that, you see, we improve the standard deviation substantially, 4.33, which IMD is 5.01. Okay, huge. And look at the synoptic and ISO variance. Okay, this is, I mean, you don't have to go into the detail. You just look and see who is odd man out. You can tell, this guy is totally odd man out. Okay, and see, moment you improve the synoptic variance, you see your northward propagation is happening. Okay, here it is not moving. Okay, so they are all tied up. What he was telling, and also it improves your mean rainfall cycle. And this actually I want to tell you. Look at this. So this is what joint PDF. Okay, joint PDF of Velar and precipitation by model and observations. Okay, so so what does it mean? Say, so shaded is observations. What does it mean? It means that, see, in observations there are even cloud which is generating Velar of 140, 160 watt per meter square and producing all these types of rain. That is the area, right? What model is doing? Model is ending here. So model is not able to produce Velar more than 180 watt per meter square. So it is struggling. Okay, this is CFS default. When you use SPCFS, this is stressed. Okay, this is this so deeper clouds are being generated. So this is for, I think, one is for India, another for global tropics. You see here. Okay, so here it is stopping here, but here, you know, the contours are reaching out to observations. Okay, so this is what this SPCFS is doing. But the problem is, yeah, I'll skip it. So, you know, all centers were doing SP at one time. And it also helps in extremes. Okay, there was a paper where you can see that SP-CAM and this is CPC. You can see all the extreme PDFs are catching, you know, SP could catch the extremes. Okay, but the problem is this was extremely expensive. We were not able to, you know, run it. We could run it for 7 years and got this paper, and that was the end of the game. Okay, we could not. So what he was telling, we went back to modifying the convective mass flux of Arakawa, play with Arakawa words again. Okay, what we found is that Han and Pan, the mass flux distribution was not proper. It has to be what you were showing. And then also we saw that why the models are producing too much of convective rain. It's because, you know, again, we learned from, you know, this cloud resolving model of, there was one Lim, 2011, he did his PhD thesis, and he showed that, you know, this, there is a fraction, okay, all GCM does. How much of my cloud water, what fraction of it will be converted into convective rain? It is decided. It is hard-coded, okay? So in CFS, what we found, it is constant. All rain, okay? But this cloud resolving model says no, above the freezing level, above 500 hectopascal, it should decrease in this rate, okay? Exponential T minus T0, blah, 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 which is less than T0. T0 is the 0 degree isotherm. And when it is more than that, within boundary layer or within below the 500 hectopascal, you can still use it as a constant, okay? When we do all these things, the mean state actually improves. You can see the ITCZ has gone. Okay, but then further, when we see the, you know, analyze further, we found that it is actually happening mostly due to convective rain, and it is even clear in the diurnal PDF. You see, this is the total this thing. This is the diurnal PDF. Okay, the trim and the revised SAS, what he was trying to show, and you see they are very good. Okay, the default one shows, you know, like a hockey sticks. Here you find the diurnal actually becomes realistic, but actually it has happened due to convective rain PDF. The stratiform rain from the same modification of convective parameters, it still looks like a hockey stick. So then further improvement. What we do, We took another paper of Wall et al. 2013. There were so many papers during that time, 2013. There was a paper group of, from Bjorn's group, okay, Kathy and Bjorn. So they all suggested that cumulus congestus plays a big role in okay. And as Mitch suggested and many other papers, that our model doesn't have this cumulus congestus, the mixed phase, okay. So we tried to add that, okay. So when we saw the plotted the trim VIRS data for Indian region, we saw a huge, percentage of cumulus congestus during the noon time, which actually will give rise to your ice cloud, further development. So when you see from Smiles ISS observations, you can see this is ice cloud here from observation, and these are all models. None of the model captures the diurnal variation of ice cloud, okay, because of this missing of cumulus congestus. So these are all paper. This is by my student. This is by Weinegger and Steven 2013. Then Wall et al. 2013. They all suggested that you should have cumulus congestus mixed phase cloud in your model. If you don't have, it looks like this. Okay, you have low cloud, you have high cloud, in between nothing. Whereas Frank Lee suggests from JPL that a cloud looks like this. Okay, and there are satellites that measures this. Okay, so anyway, so we built a strategy. We made convection, we made microphysics, and you suitably changed the radiations with all these things. And then what he was showing, I added his reference. So the model improves. Okay, the internal variability improves, the variance improves, many things improves. But question is extreme. Where is my extreme? Okay, so this is the observation from extremes, and we are nowhere there. This is Kerala 2018. Black is observations, and different color shades of different lead time, day 1, day 2, day 3, day 4, day 5. You see the models are not capturing, okay? Even though 24-hour it is capturing, beyond that, it is not. It is 2018. 2019, story is same, okay? So question is, and that this actually he was showing, this was nothing but, if you remember Peter Webster's paper on Pakistan flood, okay? He plotted the same thing. He said that ECMWF could predict the event 1 week in advance. But the problem is, see what has happened, what we see nowadays, okay? This year it happened in Bishakhdatta. 2005, 26 July, it happened in Mumbai, okay? And Uttarakhand, everywhere. So what Surya was telling that, see in monsoon, if I ask you, 2 standard deviation of the seasonal mean means what? You will tell it's a flood year. 1 standard deviation is considered to be anomalously high, right? What is happening in extreme nowadays is 20 sigma. It's a madness actually. Yeah, I mean no model on earth can capture a 20 sigma, 30 sigma. What is this? I mean, you cannot find any model. Forget the AIML. Our science has not yet come up to that stage. That's what we are experiencing. Now, you cannot tell this to IMD. The problem, our perspective is, we don't just do research. Our research is get driven by requirement by IMD. I cannot go back and tell IMD, so this rainfall is 20 sigma. No model on earth can predict it. You tell this to public. No. So you have to devise some methodology. So what is that methodology? Methodology is this. Forget the observed this thing. You come to model domain and you see 99.9 percentile means what? What is that value? You tell, oh, that is 3 standard deviation. I said, that is model's extreme. You tell, if this happens, you tell extreme is going to happen. Forget what is happening in the reality. That's how we manage, okay? You can say, no, this is not correct. But that's what we have at our disposal, okay? But if we do that, you see, it's not that bad. You see, this is a probability of 1 standard deviation, 2 standard deviation, 3 standard deviation. The blue is actually the observed rate, okay? You see all model, ECMWF and unified model and GFS, they're actually capturing. So see, a shopkeeper, a common man on the road, if you tell, you are going to get 95th percentile, 24.5 centimeter rain, he will tell, what does it mean? What I should do? I should close my shop, go home. Okay, so they don't understand. You tell an extreme, okay, rarest of the rare event is going to happen, close the school, close the shop, go home, then they understand. This is enough. This message is enough for disseminating the information that extreme is going to happen. Okay, okay, and okay, this is percentile based forecast. This all work well. Okay, we also added this recently, extreme forecast index, EFI. That also works well, but this doesn't give you the amplitude. Okay, this all gives you the qualitative information of extreme. Okay, I will just skip some of the slides. Now he was talking about the, very quickly, stochastic multi-cloud. We found that this also works, needs to be included in our model. So we did that, and because the model doesn't have the conjectures, if you plot the heating, baroclinic 1, 2, 3, you will find baroclinic mode 3 is missing. Okay, you will find 1 and 2. 1 will be too strong. Plot it. From my slide, you do it. These are all your homework. Okay, so we thought, okay, so let us give 1, 2, 3, okay, and let us give the transition probability of this 1, 2, 3, baroclinic mode 1, 2, 3, from where? From radar. So you take radar data, compute the transition probability, each grid, microgrid, and each one is associated with one heating. Don't depend on closure, and ask the model to take it and go forward. Does it work? It actually works. It actually works. You see here, this is the convectively coupled wave, this is the observation, and this is the CFS with multi-cloud model. You can see all those missing powers, they have appeared. Okay, in the rightmost column, you see they are not there. In the leftmost column, they have come. Okay, and more importantly, when we added the, you can see these papers. If you when you add the shallow cloud as a fourth mode, it actually improves even the this biases in the low cloud by stochastic. Okay, so to-do list in extreme precipitation. I'm coming to the end in another 5 minutes. Yeah, so the issue is the location, the time, and the intensity. 3 things. Okay, and so this is the paper appeared yesterday. Okay, and from our group, what actually it is written in the abstract is the simulation of associated cloud optical parameters is poor at all lead times in the model. The model also fails to capture the observed relationship between the frequency of extreme precipitation and the deep convective clouds without showing any correlation between them at all lead times. This is a disaster. This is a 12-kilometer model operationally now we are using. Okay, but this is fact. We cannot hide it. We are here. Okay, so based on these and based on all our lesson learned, we have come up to this model, which is now in, if you go to GMD, you can see the discussion is on. One review we have received, other one is expected. This is TCO grid. So this is the grid which produce very high resolution in the tropics, 6.56 kilometer. Okay, and then we run a aquaplanet, and then you add orography, then you add vegetations, test it in held Suarez mode, only dynamics, no physics, and then finally you get a full model. Okay, that's what, and now one versions they are also using. So TCO is one framework where we can avoid this, so many S, L, XL, double XL. You can use one free size. Everybody can wear one t-shirt. Okay, so TCO can fit anybody. Okay, yeah, and here one good thing what we are finding is that the tails, the extremes, this fellow, the blue, which is actually the TFS TCO, it is trying to capture the observations. Okay, that's a good thing. And we also find that TCO is holding the rainfall. Okay, the heavy rain is as he was showing. So we get till day 5, we are finding the GFS is fading out. You see, GFS by day 5 you can't see any rain over central India. So this is so now last 2-3 slides. Where do we go from here? But TCO also, in one of his slides he mentioned it takes huge HPC cost. Okay, so we go back to super parameterization. Okay, so this is hybrid. Okay, so what we are planning now is that we have SP. ready with us, okay? And you take the tendencies from SP, okay? That's basically, that's what your parameterization gives to GCM. Your GCM doesn't want anything. GCM is very loyal. It just needs, moisture and heat source and sink. You give that. You take that from SP. You run the SP just for 6 months. You don't have to run it for 6, 7 years. 6 months, it gets saturated, okay? Store the tendencies. Store the tendency of all CRM. You have millions of tendencies. And they use those tendencies to build your deep layer and train it for each, GCM grid, okay? And produce the trained tendencies, okay? Switch off your closer. Get rid of Arakawa, okay? It's gone. And that trained tendencies, you use it to, for your forecast. It will, this model will run in your, mobile memory, high memory. It can run, okay? So this is the figure from Pierre Gentin. I don't know whether it works. So what he showed, Pierre's, it's an aquaplanet, basically. So, sorry. So it's not working here, but anyway. So he showed that, SP-CAM, Velar, and precipitation rate, and from neural network based cloud brain Velar, they all look very, very similar. But they have done it for aquaplanet. They have not tested it in a real GCM, okay? And so there was, Surya was mentioning about that we have to initiate some study. So there was one study by again Siddharth to use a deep convection trigger using AML. And we found that you just use two things, brightness, temperature, and rate. And after the training, we found that yes, the model is working really good. See, this is because I am in Bhubaneswar now, Berhampur. Last year, this has happened. Okay, so we have to actually the challenge is we have to reach here. We have to predict this. So till 2:30 in the afternoon, people had no idea what is going to happen by 5:30. Okay, in just 3 hours, 18 centimeter. Can you imagine? 18 centimeter rain happened in 3 hours. Okay, so this is the kind of things I was mentioning. That's what is happening, and we are nowhere near. But we hope that this hybrid approach will provide us. This is one example of not just blindly depending on AIML, that AIML is a messiah, will solve all my problems. This is the plot of same 2018 flood by GraphCast and ForecastNet. You can see that in day 1 and day 3, it is nowhere near the observations. There was a AMS webinar, I don't know how many of you attended, by Pierre Gentin and Anna Barros on 7th November. It is a little late night, 11:30. And I attended that. I wrote a question. Time was over, but they were kind enough. They replied, sent the reply back from Pierre. I asked Pierre, there are events we are facing. The return period is 1 in 100 years. How do you train? How do you build your regression model for an event whose return period is 1 in 100? So he said that if we have data, we don't have data, okay? And he said that if we can make some synthetic data, okay, that's another way. But of course, tropics is a big challenge. He also told in that webinar very, very specifically that they are not successful in seasonal prediction. They are not successful in extended range prediction till today. They are not successful in climate prediction. So I feel, and my friend in SMW, Peter, he says even to build a reliable AI model, you need a good NWP model. So NWP will remain there, but we have to intelligently use AIML as I showed, okay, to improve the fidelity of model. Now homework for all of you. I feel this is a plot, okay, of relative humidity, rain rate, and pressure in one diagram, okay. So this shading is relative humidity, okay. What is x-axis? Log of rain. What is y-axis? Pressure. What does it show? It shows that when your relative humidity in the boundary layer is slowly increasing, your rainfall rates are also increasing. One means log 10, 2 means log 100, right? So basically, the rainfall, it builds, the relative humidity builds slowly in the boundary layer, rainfall also builds slowly, okay? This is the moist convection in atmosphere. What happens in model? First of all, there is a dry layer sitting which will obstruct your deep convection to happen. So your convection will remain shallow. There is no buildup in the boundary layer, but suddenly your relative humidity becomes very deep, okay? And it becomes like 90% or something more than that, and you get very heavy rain, okay? So this gradual, buildup of moisture in the boundary layer is missing in the model. Question is, can you do that? Can you train your model? Can you nudge your model? We have a very nice reanalysis, by the way. So homework, do it. And this, I have some CFS, take CMIP 5, all models same. Take CMIP 6, all models same. So, and the last but not the least, there is another, I will not go into the detail, you can read the paper. There is another term called precipitation efficiency. Models are miserably bad in precipitation efficiency. You can do that. So, the remarks is this, that ensemble and probabilistic forecast is doing well, no doubt, particularly in the absence of a realistic representation of cloud and moist process NWP. Possible way out is that further model development, okay, and moist physics, stochastic, scale-aware, data-driven, convection permitting, okay, in one line. Novel approaches that as I showed. And the last point, I don't know who will prepare this data, a high-resolution spatio-temporal observation data, which Surya mentioned at the end, that will help us in downscaling and bias correcting at the location specific. Thank you.
Thank you, Professor Parthasarathy. I think we have time for questions. Why don't you grab that mic and pass it on? Yeah.
Thank you, sir.
Yeah.
My question is,
Take your time. I have given a lot of food for thought. I am here whole day.
could you please elaborate more on what is superparameterization?
Okay, that is in the break. I cannot elaborate here.
Thank you.
Yes. Any other? If very specific, short question and short answer. Otherwise, we have lunch, dinner, tea. Hi, Eric. Oh, you are asking. Yeah, please go ahead.
It is working?
Yes, working.
Yeah.
Yeah.
So almost all the models have a constant relaxation time, right? When they do the parameterization.
Yes.
But in the real world, you don't have the constant relaxation. It keeps on changing with time. And it keeps on changing with space.
Right.
So was there any attempt to actually look into this constant?
We have not done it.
Yeah.
But definitely you can do it. Yes, sure.
Yeah.
Yes, Deepesh. Yes. Hi, Eric.
So you talked about the advent of AI for accelerating progress.
Right.
You also mentioned, some of the problems regarding moist physics and parameterization have been around since the 1940s, with Charney's paper. So what would your advice be to a young scientist? Should they spend any time trying to develop a convection parameterization from first principles, or should they simply rely on AI approaches to improve parameterizations?
So definitely from first principle. You see, my suggestion to all of you is that don't even touch the model first. Okay? First, look at the observations. All discovery has happened from observations. So first look at the observation, look at the field experiment, look at the reanalysis, build a new hypothesis first. Without that, you cannot, by doing this sensitivity, blah, 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 you cannot solve any of these bottlenecks, for sure. Richard Johnson, 1999, is the basis for all this multi-scale clouds. Okay, it comes from a field experiment. So please look at the field experiment. Please analyze the reanalysis from first principle. Test your hypothesis and then start going step by step to solve some of these existing problems. That is what he is telling. I fully agree with it. AIML, as I showed you, it has its own limitation. I don't know if some of you, those who have attended this talk of Pierre Gentin on 7 November, the AMS webinar, he was very, very clear. He was telling we are till today not successful in extended range, we are not successful in seasonal range, and we are not successful in climate. So they are only competing with IFS day 1 and day 3. Forget it. So don't get carried away, okay, by AIML. It is a tool, basically, just a tool. Don't allow your mind to go, blow away with this AIML. You use it consciously as a tool, but don't leave this first principle approach in solving this problem. This is an age-old problem. Charney also realized, I also realized, you also realized, we are good. We are the same boat. But then we have to go forward. AIML, of course, not the way to take us forward. Yes. Any other? Let them think. Vishal, yeah, go ahead.
How we trust ECMWRF is accurate, like reanalysis data we are using as a observation,
Yeah.
but they're also developing one model and those are giving the output. So how we have to trust?
See, no. So see, ECMWF, they have, you should go and read their technical notes. Okay, ECMWF doesn't publish paper. Okay, so what I will tell, why we believe, why everyone believes ECMWF, to know that you should please read their technical notes. You see what they have done. What they have done now, in 2025, they are going to bring ERA 6 reanalysis. You read, already documents are available, what they are going to do in ERA 6. Okay, so they are physics, they are assimilation, initial value problem, they are master class. Whatever is available, you take the best. I'm not telling they are the ultimate. Okay, tomorrow somebody else can come up with, but till today, there is no one, which can give us this representation of the mean state as we get in ERA 5. Yeah. So they are doing that. They are doing that. ECMWF is very conscious. For example, this Aola satellite was sent, for what? All reanalysis was very bad in low-level wind. Okay? Because we were not having any satellite which can measure the wind. So there was a huge debate. It went from NASA to ISRO, ISRO to ESA, ESA to JAXA, and so on and so forth. Finally, ESA could send Aola satellite with a LiDAR that will probe the low-level wind. ECMW was the first to assimilate that. There are papers now in QJRMS. You can see that. So you've improved. So there is no point in disbelieving them, right? Yeah. Anything else? Question? Oh, hi. Maxim, please.
So you
Yeah.
you clearly showed that if you rely too much on CAPE in the convective parameterization, then you tend to have too often precipitation. But I think some people have also tried to include some dependence.
Who's that?
I know about the IPSL model, but I think maybe some others. They have tried to include also dependence on SIN to also maybe make sure that the trigger is not based on CAPE, whereas maybe closure might be based on CAPE to some extent.
True. So see, all these switches, whether it is CAPE or SIN or RH or this and that, okay, this will see, if something happens good for India, we really get excited. And I will tell you honestly, I went many times to ECMWF. I asked Peter, please suggest what you guys are doing. Our models are not doing very great. He's telling your models is doing much greater than what we are doing. We are interested over UK and the Queen. We are not. Honestly, we will never able to capture 50 centimeter rain or 40, whatever. We stop at 5 centimeter. Okay, so you are doing much better. Don't ask, don't tell us. So this was the discussion between Niels Swedy, Peter Bechold, and myself. Okay, so my feeling is that all these plugs and switches can, make you and others happy momentarily. But if you want to really see a paradigm change in the mean state systematically, this K-pens in business may not help us. What Eric is telling, we have to start from the first principle, but we should support it by reliable, observation data and a very robust hypothesis. That is missing. We don't have any closer, right? We could not. Since 1974, we are still using the CQE after knowing that it doesn't work for tropics. Pitiful.
Yeah, I have one question.
Yeah, please.
So I think in both first two talks, it has emerged that synoptic scales are the bottleneck. At times, teleconnections have improved. At times, small scale representations, local representation of cloud development has kind of played a key role. So my question is, so if you ask somebody who looks at mechanisms, they would say synoptic motions derive energy from the background flow.
True.
So if you have right background flow, one would expect synoptic scales would emerge out of the background flow.
True.
And on the other hand, small scale probably would want to feedback into the background flow.
Very true.
So,
but there's a catch.
Yes.
There's a catch.
Yes. So please.
The catch is, do you have a paper? So you can do it through energetics very easily. One of my colleagues in IITM Sahadat has done this. The problem is this conversion again. Okay. So you have an MKE. Okay. You expect that when a depression forms from my mean state, actually mean kinetic energy should be converted into eddy kinetic, right? But it will not happen. It will not happen. So if you go and take CFS sine cast, you go and take 20 years GFS sine cast, as Surya was telling, so these model data are available to all of you, okay? You don't have to spend a single rupee, okay? At least 30 years, 20 years, we have made this much available to all of you. Just drop a mail to ADRC or just register, I think, not even email, right? So the point is that this MKE to EKE and various other terms, it doesn't happen, If it happens wrongly. When actually EKE to MKE should happen, that time you will find MKE to EKE is happening. Okay, all sorts of odd things happens in model. Okay, so the issue is the energetics or the different modes. Okay, they are again not listening to the nature. Okay, so there again I will suggest that. So these are the bottlenecks actually. These are the bottlenecks. You try using AIML. You try using AIML because my benchmark is ready. It does in era 5. Our always benchmark is era 5. In era 5, MKE to EKE happens, okay, but not in model. And it is irrespective of any model. So that's the issue. But what you are telling is very true. So we expect that if my mean state improves, my synoptic scale variance will improve. It's not, because the model is not able to do this, conversion in the right way. That's the problem.
Is it fine to say that there is a need of systematic diagnostic at mesoscale?
Absolutely.
How very small scales feed energy there, how very large scale?
You are on the dot.
Okay, yeah, thank you.
So what Daihun did, a CLIFR diagnostic. You do it for monsoon mission, a mesoscale diagnostics.
The background flow you are mentioning, it could be large scale, also mesoscale. So unless what is our understanding so far is that mesoscale background still missing in the models.
It's missing. That's what Mitch Moncrief also mentioned in BAM's paper. Yeah.
So background is not large scale alone.
Right. Because I've seen Nilin was one of the, I think, co-authors. There's a recent paper on just diagnostics focused on probing this sort of a thing. Maybe we would want such a thing.
Yeah, it will be very good. If you can build such a diagnostics and like CLIFR diagnostics, you make it public for all the students to play around, they will get a very good, learning. I agree.
Other questions, maybe short one?
They're tired.
Maybe it's time.
They got too much. I'm maxing.
You also showed some examples where you use the microgrids. You use the microgrids
Micro?
Yeah, you use the transition from state to state. Within a grid, you subdivide in smaller grids.
Okay.
And you
Yeah, that is for stochastic multi-cloud model. See, what happens is that, say I'm using a 100 by 100 kilometer grid. And as I showed in the in some photographs, right? So there are various types of clouds, right? Shell clouds. So think about Arakawa's schematic, some deep cloud, some conjectures, and so on. Now, question is, the stochastic multi-cloud needs transition probability for each small microgrids. The question is, from where do we give that? So there we do a radar-based from observations, okay? And you have this baroclinic 3 modes defined, okay? So that sort of things, that is done in that stochastic multi-cloud model, Andrew Maida and William Quider, and yeah.
Do you think this is a substantial change in paradigm, as you are calling for, or is it still within the existing family of
okay, so 2 things I'll tell you. The stochastic multi-cloud model, what we have seen is very good in improving the mean state, no doubt about it. It is also very good in improving the convective coupling, okay? But still we have not seen, or we have not tested how good it is for extreme. That's what is my topic. We have not tested it. That is, again, there is no guarantee that my model mean state improves. And, yeah, by the way, it improves the synoptic as well. But still, in the last slide, I said that precipitation efficiency, that is another huge, subject. So we have not tested. So it is, so stochastic multi-cloud model still trying to, represent the convection. It is still not touching the, clouds per se, okay? So it improves a lot, okay? It improves many things, but possibly not everything.
Are there any other comments? Maybe if not, then let's thank Professor Parthasarathy once again. And let's break for tea, and we'll reconvene at 11:45. I have requested the next speaker who's going to give an online lecture to start at 11:45. So quick tea, and we are back.